Hello, my name is Paul Stanek, and I was in charge of the sensing part of our project. Basically, for AutoGuard, we were going to have 3 different sensors collecting 4 types of data. We had the pip tags, which were going to collect light data, the soil moisture sensor, which was going to collect the soil moisture data, and the DHT22 Arduino Raspberry Pi sensor, which is just a simple little sensor that can detect the humidity and temperature. Now, the pip tag could also collect temperature and humidity, but you had to calibrate it and it was inaccurate, so we did not want to use that. One of our bigger problems that came up was the soil moisture sensor. After meeting with Rich Howard, he stated that the resistive soil moisture sensor would go through electrolysis and corrode after a while. After doing some research online, I found this to be true. What happens is eventually it becomes so corroded that it'll just become inaccurate and you'll have to change it every week, or depending on what program you write, you would have to figure out a way so that the soil moisture sensor wouldn't be running continuously. But obviously we want our garden running continuously. You have to monitor these things a lot. So we came to the conclusion of using a capacitive soil moisture sensor, which unfortunately didn't come in time due to the virus. For the pip tags, we just were going to have the receiver plugged into the Raspberry Pi, which would have been in the garden, and the collector inside the garden. We were going to use 2 pip tags, one on either side of the garden, or one on top, one on bottom. We didn't figure out the orientation yet, but this would have provided more accurate data reading. The DHT22, we would have had 2 of those as well, one on either side of the garden, and those would have been running continuously. Based on the input from the user, this data would be read, and if statements would be written in Python to determine what to do with the said data that was collected. For example, if the water was too high, we would stop adding water. If the water was too low, we would add water. If there was not enough light, if light was below 50, we would turn on a light. The idea here is that it was kind of like a smart garden, in that it would work for you and be continuously monitoring your plant when you had to be away and could not be there. So yeah, this was pretty much the sensing part. Thank you.
Hi and welcome to the AutoGuard website. The main purpose of this website is to act as a facilitator for users to input different parameters or settings for the device. This goes along with the Android app, and it's where a user would go in order to control their device. Right now we're on the home page screen and it's pretty simple. It really just has a bunch of data and information that tells users what they might expect from this project and what it's best used for. In order to start using this website, we first have to register an account, and the process is pretty simple. You just have to put in an email that hasn't already been used. Okay, after registering, the next logical thing to do would be to log in. Okay, after logging in, the first thing we notice is that we have more options at our disposal. The most important link right here would be your devices. Right off the bat, we're going to notice that we can't really control anything because we haven't linked anything to our account. The linking system works pretty similar to how an iClicker would work, where an iClicker has a unique ID, so every device should have its own ID, and for this testing demonstration, I have 6,000 set up. So after linking the device, we can now see a little more information about it. We see its version number and whether it's on or off. So the version number goes to the device information page, and it just shows you a little bit of information. It's kind of simple right now, but it just tells you what to expect from a certain version of your device. So Going back to the device page, we now can get an in-depth view of it in its control panel. As you can see, we have 4 different settings that can be controlled by the AutoGuard. The values that you set here are basically what the AutoGuard will compare its sensor data to, so it knows whether any correcting action needs to be utilized. You can play around with the numbers, and the next time AutoGuard makes a check for the parameters, it's going to run its data against these numbers. So as you can see, saving it would upload it to the database. Underneath it has data that the Raspberry Pi collected. The Raspberry Pi will periodically collect this data and save it to the database so that we as a user can view it in the form of a graph. These can be pretty useful because users can view trends, daily trends they might see about their device, and they might be able to analyze the environment of their plant. Other than that, we have user settings page, which just lets you edit information about your account, and a contact help form in case users need help for something. And that is the site.
Hi, my name is Vincent Chang, and my part in this project was assisting in the development of the hardware for the AutoGuard. I have worked with Karthik in developing the hardware prior to the quarantine. Our main goal was to design a circuit that would be able to receive a signal and then output the corresponding data or signal to the user. After we do so, we plan to connect it together with the software. We've tried testing out various ways to connect the sensors using Arduinos, Raspberry Pis, or using MOSFETs. We started using basic circuitry to figure out how to allow a signal to pass through a MOSFET, whether the signal was high or low, by using a breadboard. We initially used a TIP32C MOSFET transistor to test out what output would be shown after given a specific input. After much trial and error and further research, we decided to switch to using a Raspberry Pi instead because it would provide more data to the user. We worked with our professor and TA in figuring out the most optimal way to configure our circuit with the Raspberry Pi. One of the bigger obstacles we had to overcome was trying to get the relays to work correctly so that the sensors can accurately output the correct signal. Unfortunately, our progress came to a halt due to the outbreak that has occurred, so we were not able to fix all the kinks in our circuit, and we were not able to embed our hardware design with the group's software design. As mentioned before, we had hoped to contribute more ideas to circuit designs before the whole outbreak occurred. So between me and Karthik, this is our process for our circuit design and any future plans we had hoped to accommodate into our circuit design.
Hello, my name is Karthik and my part was the hardware for AutoGuard, our smart garden. When we were working with the hardware to make AutoGuard, we first planned out how we were going to make it and with what. So I started off with what our overarching goal of AutoGuard was, and then how my part contributes to it. Then I looked at what exactly that goal was. In this case, that was outputting data to the user. Then, after looking at the hardware plan from the top-bottom view, I started thinking about the bottom-up approach, which in this case was starting with the breadboard, Raspberry Pi, sensors for input, and the relay. We made the circuit connecting the Raspberry Pi to the breadboard and the sensors, and then we planned out how we would connect them to the relay for negative feedback and the MCP 3008 ADC chip, which would be used in conjunction with the Raspberry Pi to read, collect, and visualize the data from Raspberry Pi to the sensors. So the Raspberry Pi does not come with its own built-in ADC chip, so we would have to use that along with the Raspberry Pi. Now, due to the virus, we were not able to build the whole hardware part and embed the hardware and software parts together. But what we were going for the hardware part was to connect the Raspberry Pi to the breadboard, connect both of them to the MCP 3000 ADC chip, and then connect all three to the sensors and a relay. Now, had it not been for the virus, I would have wanted to add an irrigation system, a lighting system, and a micro temperature configuration, all built using like circuits, and maybe get some help from a professor and see what I can do to build it for a self-sustaining garden. And along with machine learning algorithms, since I took 2 courses on it and I have working knowledge of the theory and application of them. So once temperature or moisture or an amount of light is detected, if all of this is added on in the future to our smart garden, then let's say that once everything is measured, you have some things such as temperature or water amount in a plant, and let's say it's below the average range or below the desired range or value that the user wants, right? The relay system would factor in and activate the irrigation system to add more water, or even affect the water temperature before it gives out water. And then I would employ a machine learning algorithm such as principal component analysis to visually represent the connections between, say, plant death with a current rate of some parameter to improve performance, or the desired range of, let's say, moisture. So for example, I would employ this PCA algorithm, which would visually represent the connection between which parameter, like let's say how much water you give to a plant and how it contributes to the deterioration of the plant or its worsening conditions. So it's a way for you to see what you should be doing to keep it alive and not like let it just die. Another future plan, or if the virus didn't curb the completed hardware as was planned, I would have implemented another machine learning algorithm, but this one would be a linear regression method that would predict different features of the plant based on previous plants' growth of the same species. I would say that this is something that would be very beneficial for everyone that just wants a smart garden or wants to do their part.